Okay, as the semester's winding to a close here, we want to fill out and figure out everything about every chapter. Here I'm going to start with Unit 6 review, and it's just going to be specifically on two-column proofs, but the good news is that it's going to help talk about kind of all the other vocabulary that fits within here. Well, at least give and take. It'll include some of them with the two-column proofs. This is just a good thing to practice, though, especially if it's something you weren't good at in the past. Something you can look at here and there. I have seen some portions of the final, and although it's not covering two-column proofs extensively, there are some portions of it in two-column proofs, and this also talks all about all these other things here. Now, I will apologize for now. My voice isn't at its best. So if it's a little difficult to listen to, make sure you take some time, you rewind, you clear it up if there's ever any trouble. So the top portion that I have right here, which for now I'll ignore and I'll kind of go back to if I need to. In a two-column proof, you give statements. You're trying to build up evidence to prove something. Like here, let me just go over to a proof right now. I won't do it. But you prove triangles congruent using statements. You're going to say that some segments and angles, some parts are congruent to each other for a specific reason. And that reason needs to be verified in evidence. You need to have actual evidence to support that statement. So if you're going to say, in this case, that JM is congruent to KL, you need a reason behind it. In this case, it's given. And that's one of the reasons that you can actually give in a two-column proof. This isn't all of them, and there are some that are really kind of super specific that I didn't cover in here. And if you want to fill them out, if we run into them, we will, which is fine. But until then, I left some blank spots for you, and here are some reasons that I know we're probably going to run into here or there. Same with the angles as well. There are a few more because there are those parallel line things that you can have from time to time. So there are some angle ones. When you say angle A is congruent to angle D, there might be a reason. Maybe they're vertical angles, whatever it is. So that's what all that stuff up there means. And other reasons that you're going to run into are when you make your triangle congruency statement. So you might have a congruency statement that says triangle ABC is congruent to triangle DEF. And there are only 5 reasons that you can actually even give to make that true. So here's what I'm going to do. And on your paper, if you're going to draw this as well, you want significantly more room to draw a set of triangles. But I'm going to have 2 triangles here, which they are drawn to scale to be congruent. They might even be equilateral, but that's besides the point. I'm going to name one triangle ABC and one triangle, and I'm going to do this a little differently. I'm going to put them into different spots because, again, don't assume they're drawn to scale. I can put DEF here. There's going to be another bell after this, so go ahead and ignore that as I'm going to talk right through it. So what if we said triangle ABC was congruent to triangle DEF? Then that means that there are congruent corresponding parts which match. Angle A is congruent to angle D, so whatever's going to happen here, angle A and D will be congruent. Segment AB will be congruent to segment DE, so you're going to see, whoops, that's not AB. You're going to see AB right here and DE right here that will be congruent. Angle B is congruent to angle E, so here's angle E and here's angle B. Segment BC will be congruent to segment EF. And then angle C is congruent to angle F. And segment CA, or AC, is congruent to segment DF. So here's DF, here's AC. So even though these are rotated in a different fashion and you can't necessarily see and go like, oh, well, I can exactly see how they're matched up, normally you'd want to rotate one of these triangles. Like I'd take this whole triangle here, minus that C. But I'd take this entire portion right here, and then I'd rotate it around so that it matched. Like this would be DEF now. And now you can see how here's DE. I know the letters are rotated, but look at DE congruent to AB, EF congruent to BC, and FD congruent to CA, and the angles match up as well. So you'd always want to work to that and say, okay, now I see the matching parts if you have to, and if there's a way you can physically do that. I can do it obviously a lot more easily on this computer when I do this here. And the other important part about why I just did all this is because if you have a congruency statement such as this and it's true, maybe they give you it's true or maybe you have to prove it's true, then you can make the statements that I made. You can then say that angle A is congruent to angle D, angle B is congruent to angle E, and angle C is congruent to angle F, and the segment AB is congruent to segment DE, segment BC is congruent to segment EF, and segment AC is congruent to segment DF. These 6 things that I listed are all a part of that 5-letter thing called CPCTC. So I'm actually going to do more up here. I just want to go with the flow that I'm on right now, called CPCTC. Now CPCTC stands for it's an acronym for the following words: corresponding is the C, parts of, which isn't a part of it, congruent triangles are congruent. What this means, and I'm going to write it in different words. If you substitute the word corresponding for matching, for parts we say sides and angles. Let's keep the of. Congruent triangles, I want to put identical triangles. Are congruent. I want to put are, instead of congruent, I want to use words you'll use, the same. So even though this sentence might not make sense, corresponding parts of congruent triangles are congruent, how about this? Matching sides of identical triangles are the same. Matching angles of identical triangles are the same. So if I have 2 identical triangles, like twins, right? I have 2 twins here. And remember how they actually match. You have to correspond parts. They have to match up with one another. D has to match with A, because A and D are the first letters in that statement. So D and A match, B and E match, C and F match, and the segments in between match. If the triangles are congruent, if all you have is the statement and you're not told these other things, but you know the triangles are congruent, then that means that those matching parts are also congruent. D and A must be congruent because triangle ABC is congruent to triangle DEF. Segment BC must be congruent to segment EF for the same reason. If the triangles are identical, just like identical twins or whatever, pretend like they're clones of each other, then there are parts, then that person's left eye, if it's like 2 inches wide, I don't know how wide eyes are. If they're 2 inches wide, the other one's 2 inches wide, everything like that. The person's 5'4", the other person's 5'4". Whatever part you're looking at has to be exactly identical, with one exception, and that's the letters. Just like a person's name. Twins Ryan and Brian. They're all the same except one's named Ryan, one's named Brian. Okay. So that's basically what CPCTC is in a nutshell, and I want you to go and look back at that or pause this screen. I'm going to hold it for 5 more seconds because I'm going to erase that stuff up there and redraw these and talk about these 5. Okay. Now that's not a good definition of CPCTC, and thankfully on the test you're not asked to actually define it, I don't think, but the understanding is more important, and I hope you get it through there. So I'm erasing everything here because I just want to get the triangles in there. Of course, I could have just redrawn the triangles as well. Maybe that would have been better. Either way, okay, we're back to where we started here. I have 2 triangles, ABC and DEF. Let's say they were congruent. They're congruent because of some conjecture. You were able to prove and build up a proof to say that these were congruent. Maybe it was from ASA, which stands for angle side angle. And I'm not going to write out all of these. I'm just going to do this one and then probably one down here. Angle side angle means that, like, let's say you found out that angle A was congruent to angle D. Now, you needed a reason behind it, even if it was given. And let's say you found out AB was congruent to EF, and then angle B was congruent to angle E. And then you could say, okay, triangle ABC is congruent to triangle DEF because of angle side angle. First of all, here's what the drawing means, is that you had these congruent here, you had these congruent here, and you had these congruent here. So you draw that on there. And then it says angle side angle means these are congruent. That's your reason behind it. The reason why you can list that reason is because these 5 congruency conjectures here are unique, bare minimum pieces of evidence that you can stack together to prove that the triangles are exactly what they must be. Okay? And it's hard for me to actually give you counterexamples because there's no way that these can be false. But let's say that I kind of redraw this triangle here, ABC. Now, the things that I have to keep true in triangle ABC are this length needs to be exactly this, and this angle needs to be exactly this. Now, tell me a way where I can redraw this triangle to change this length, this angle, and this length, making sure these have to be the same. If this is this angle, that means I have to go out this way. There's no other way I can do it. Now, I could shorten it. I could say, okay, I'll just put it right there. Boom, now I have a new triangle. The problem is, even though you have this angle, this side congruent, this angle is no longer what it used to be. So this angle still needs to be going out this way. And you're going to see that this length can't be short as well. If I have these lengths short, I don't connect the triangle. So this length has to be exactly that length to match up with this one right here. So these lengths have to be exactly that. My point is that I cannot manipulate this triangle and make it a different triangle. Once I know that these angles are what they are, and that these angles are what they are, the rest of the triangle has to match up and be the same. And that's the point, again, behind CPCTC. Once I know the triangles are congruent, then I know that the rest of the points have to be congruent. BC has to be congruent to EF, because there's nothing else these things can be. Even though I don't have it in evidence that these segments are congruent, I know that because the triangles are congruent, then these segments are congruent. And the example, excuse me, I'm going to drink water for a second. And the example that I always give, even though it's a bit extreme, is if you're talking about a court case, something on trial, where there's someone who possibly committed a murder, or perhaps a robbery too. But murder's good because you get to talk about, bloodshed. You're trying to convict somebody. You are a prosecutor, and you're trying to build up evidence. You're trying to build up this case, and it would be a slam dunk if only there was a security footage videotape of seeing the guy shoot or stab the other guy, right there in the warehouse. And you're like, if only I knew he was at the scene of the crime as well, right? If I have video evidence that I know he was at the scene of the crime, you don't even have to see the shooting. Maybe you have other evidence there. But you're like, I just need to pinpoint the fact he was at the scene of the crime. There were no witnesses, no video. I'm having trouble with this. So scene of the crime is something you cannot prove. Just like a segment. It's like, I can't prove this segment's congruent to this segment here. But what if, and this doesn't help much for your court case, but what if you found the gun, it had fired, you find fingerprints on that gun, and it matches the guy. And there are witnesses that say, he was acting out at this time, and he has this motive, and there is blood on his shirt that was tucked under the floorboard and stuff like that. And you build up enough evidence. It's like, I'm getting a bare minimum of what I need. I can't get everything. I can't get that he was at the scene of the crime. I can't get everything. Just like in these triangles, I can't get that every part's congruent, just some parts. But if you just get enough, then you are able to still convict the guy. It's like you have all that evidence, you convince the jury of I guess not your peers, it's the defendant's peers, even though they're going to say, all 12 of them go, we find the defendant guilty of murder because, blah, 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 based on that evidence we had. Now, you found him guilty. If he's guilty of murder, then that means that he was at the scene of the crime. Okay? You don't have any evidence to say that he was at the scene of the crime prior to everything else. And this evidence maybe doesn't have anything to do with the fact he was at the scene of the crime. But if you build up enough offset evidence outside of that to say he's guilty of murder, then if he's guilty of murder, then he must have been at the scene of the crime. So it's like, take this stuff, build it up to get this big idea. Once you get that big idea, you're going to get that little idea out of it. There's all this stuff and says, that means if you had this, based on knowing this, then this also must be true. So that's the whole thing behind CP/CTC one more time, and the reason why I'm saying all that is because angle side angle only gives you just a little bit of information. But if it's enough to prove the triangles are congruent, that means the rest of the parts are congruent. There's no other way I can manipulate that. So I'm going to go more quickly through the other ones, but I'll give you more examples through angle side as to why that's true. So that's angle side angle. Let's look at side angle side now, and I'm not going to write out side angle side. You can. But side angle side would mean, and here's the other reason why I have to do all the rest, is because if you have one set of things congruent. Oh, by the way, I had those mixed up. This should have been A and D over there. But if I have AB congruent to DE, and then angle B congruent to angle E, and then angle B or segment BC congruent to segment EF, I now have side angle side, the same thing. These other parts must be congruent. There's no other way I can change those angles to not have a triangle. And have a triangle in both. And those certain parts are congruent. Now, what all these mean when you say side angle side, what that means is that if I have a side, immediately following it, I have to look at a set of angles that I also know are congruent. So I can't have this side congruent to that side, and then this angle congruent to this angle, and say this has something to do with side angle something. No, they have to work sequentially. And what that means is side, immediately following that, I have to look at an angle. And immediately following that angle, I need to look at the next side. Here is side angle side. Okay? This would be an example of something that is not side angle side. Side angle side. You're saying side angle side, you completely skip this side and this angle. They must work in sequential order. You have to have parts going sequentially, side angle side in order to use that conjecture. Okay. Side is hard to avoid using that because in a triangle there are only three sides. So as long as they match up, side with side, and side with side, you have side congruency conjecture. Again, I can't manipulate the angles in any other way. So there's side angle side and side. Whoops. Okay, now I'm going to look at angle side. Now I'm going to look at it in a few different ways here. First of all, angle side could also be called side angle. And I'll show you why. It's just the way that you look at it. So here's an example of angle side. Angle A is congruent to angle D. Angle B is congruent to angle E. And segment BC will be congruent to segment EF. Okay, here's angle side. I have angle side with angle side. And again, what that means is that I'm working in a sequential order here. If angle, I skip this side because I don't know they're congruent. I have this angle. Two angles doesn't prove congruency. It does prove similarity, though. Remember, angle similarity. That's enough to say that the triangles are similar, which means all angles are congruent. But they can have different side lengths. But if I just get one side, it doesn't matter where it is. It could have been right here, it could have been there or there, but that's angle side angle. If I have just one side, that's enough to say that these triangles must be exactly what they are. There's nothing else. Now, the reason why it could also be called side angle is because I could have obviously said side angle, side angle. That didn't distort or change the picture at all. All I did was just set it in the other order. In fact, some people write it this way more. I just write angle side. I don't know why. No reason to, or not to do it either way. Okay, there's one that I want to throw out there that's not, because some people don't think that angle side is one because we make so much mention of one that also is not one, which is angle side or side angle. Most teachers will write side angle because they're afraid to write, as. But either way, angle side and side angle do not qualify as congruency conjectures. And one way to remember that is because you're saying, oh, that's a bad word. Oh, you can't use that. But here's an example of it. So I have angle side with angle side. The reason why this one isn't congruent here is, check this out. Even though these triangles are almost exactly drawn to scale, I'm going to change one of them. Now, it can be true. There's, all these can be congruency conjectures. I'm sorry, well, not conjectures, but these triangles can be true. You just don't have evidence to prove it. You need more evidence. So you can see these triangles are pretty much identical, right? So I'm going to keep those matched up exactly like that. And what I'm going to do here is take triangle ABC. I'm going to keep these measurements here. This angle must be what it is. I'm not going to draw it all the way down because I don't need to. I'm going to draw this side length. This side length must be what it is at this angle. And this side length must be what it is. But this side right here, although it needs to be this length, you'll notice it doesn't have to be at this angle. There's nothing here that I say that this angle has to be congruent with this angle because we don't have any proof behind that. So I could virtually take this side right here, and I'm actually going to clone it. I'm going to take this side length here, and and because I can't rotate it exactly, I'm going to try and be as perfect as possible with it. I'm going to move it along like a circle. Yeah, here, let's do it that way. Take a circle and make it red and dotted and thin. I'm going to make a circle right here and say that a side of this length would always be this length because it's because it's a radius. This is actually a poor side length to choose. Shoot. This triangle's too equilateral. Okay, let's say the side was about this length right here, whatever. I'm going to take this side length and start moving it along here. And eventually, let's say that it hit right there. This is still a triangle. Okay? Right here, this right here is a different triangle in green. It has a different angle right here, same side length, but a different angle right there as well. This triangle is not congruent to this triangle. And again, I'm sorry, this is a poor example because I have pretty much an equilateral triangle here. I want to do this again in a different light. We'll do it one more time. Because I do want to get this one across and explain why this is not true. So let's go and, well, not even clone these. Let's just go and do a new page. I want to make two triangles again, not as equilateral this time, a lot skinnier. Yeah, skinny triangles. You know what? I don't even need two triangles. I just need one triangle here. But I want this side, this angle, this side, and this side right here to be what they are. So again, I'm going to say that this angle needs to be this guy. That side length doesn't need to be that. This side length needs to be that. This side length needs to be that. But it doesn't need to be at that angle. What am I saying? I have no idea. But now what I'm going to have here is that circle. And this circle represents a radius to just say that I'm going to rotate and keep this side length exactly the same. It's not going to change. So here's a little circle. Hopefully you can see that. If I rotate this triangle, this side length enough, it goes along here. It's the same length, obviously, because this is a radius. And it goes right there. Now you're looking at this green triangle right here in comparison to the black triangle. So take a look at this green triangle. This green triangle has the same angle as the black triangle. It has the same, or this one, like if this is ABC and DEF, ABC has angle A and D are congruent, AB and DC are congruent, and BC and EF are congruent. Make no mistake, they are congruent. Remember, we just did this on a radius. Now, this angle C is not congruent to angle F. Segment AE is not, or segment AC is not congruent to segment DF, and angle B is not congruent to angle E. These triangles are not congruent. Angle side-side or side-side angle is not a valid congruency conjecture because I can make different triangles out of this. Okay? So that's a huge, huge problem with this thing is that while on these other ones you can't manipulate these triangles to make different ones, here you can. That's why this is not a valid congruency conjecture. You can tell, even though they're not supposed to be drawn to scale, but they are, these are two uniquely different triangles. So it's not proof to say these triangles are congruent just by this information. Now you can have side angle side, and this is why that order of how you say it's so important. If you had this congruent to this, I mean like literally, if you had side angle side, now the triangles are congruent because there's no way that, because these side lengths have to be congruent. It would have to go down there. But side angle side is not the same thing as angle side side, and the way that you say it is so important. Angle side side or side side angle has to be spoken in that way because of the order in which they're said. Okay. Now the only exception to this is HL. And HL stands for hypotenuse leg. And this only exists in right triangles because only right triangles have a hypotenuse and a leg. So if I have two right triangles here, let's say they're congruent, ABC and DEF, again, and you're given that they're right angles, or you find out in some way that they're right angles. Maybe they say it's a perpendicular bisector or something like that, and you have to know that. And you figure out these portions are congruent. You find out the hypotenuses are congruent, and that one set of legs are congruent. This is enough information, even though this is angle side side. Check this out: angle side side with angle side side. This is the one exception because there's no way to distort this into a different triangle when you have a right angle. Because the thing is I could take this AC, I could swing it around just like the other circle thing and try and find a different thing. You'll swing it over here and you're going to create another triangle, but it's going to have the exact same side length over here and everything else will be the exact same. These must be congruent for hypotenuse leg. And the other reason behind it really is because if you were given values here, say it's like 5 and 4 and 5 and 4, use Pythagorean theorem, and you'll find out that this is 3. So now you have side, side, side. You have side, angle, side. You know, or you can use trig and figure out using sine or something that this angle is congruent to this angle. You're complete at that point. Pythagorean theorem and trigonometry also can give you the other congruency conjectures. So that's why we cut it short and we say HL is good enough. If you have hypotenuse and legs congruent in right triangles here, then you have two congruent triangles. Okay, that's enough for me for the first page. I think I cleared most of that up in previous times. And try and use the next half hour or less. I really want to do this in less than a half hour. And do all these. I'm going to go bullet straight through them as quickly as possible for everyone's sake here. Okay, building statements and reasons. This is really tough for people. It is. Having them make sense and flow correctly. And this is where this stuff needs to, I'm going to delete this page. It's just getting in the way. This is where we really need to flow right here and give proper reasons to our statements. You can't make up reasons. Right? This is for anything in life. You can't just make up something. There needs to be verifiable facts. It says prove the triangle is congruent using a 2-column proof. What you're going to do is definitely work with the givens. Use what they give you first, or what they tell you and what you can draw from there. So I'm going to see some statements I have here. I can say segment ML is congruent to segment JK. Now, the whole thing behind this really is that you have to recognize where your two triangles are. I have a triangle here, and I have a triangle here. And you have to recognize the fact that when you're making these statements, it's basically you're really redrawing these triangles. If I have JKM right here, I want to redraw this triangle so that, at least for now, it looks like they're facing the right way. If this is MJK, then this is KLM. And I want you to pay attention to what I did there, how I redrew them. These triangles are now redrawn, so that's saying in these two triangles, these segments are congruent, these segments are congruent. What else can we figure out? So that's the whole point behind what I'm doing there, and why we make these statement reason things. Because these are two separate triangles. And that's where I'm going to talk about reflexive property in a second here. So I have, I can say KL is congruent to JM. That's also given. Okay, step 3, reflexive property. Let's talk about that one for a second. Reflexive property in sides means that you have two triangles, like these two right here. But in the case where they're drawn as such, kind of like a parallelogram or whatever, this side, MK, is the same side in both of them. So in this case, here's MK, here's KM, but it's the same thing. And the fact that it's being shared in this object, in this drawing right here, means they must be congruent to one another because they're the exact same length. There's no way they can't be a different length if they're the same exact thing. In two triangles, they look completely different. Here, as this drawing like a diagonal, it's the exact same thing. And they drew that. They didn't write this down for you. You have to mark that and know that yourself. So I'm going to put MK is congruent to KM. The reflexive property. Reflexive property means shared. In sides, it means shared side. Shared sides of a triangle. In angles, it means shared angle. That really only exists in similar triangles. So finally, we have side, side, side. Side, side, side. Congruent with side, side, side. That means by side-side-side congruency conjecture, triangle, and this is why it's important to redraw it, to know which parts correspond. Triangle MJK is congruent to triangle KLM by side-side-side. Again, the lettering is so important. You can choose your first three letters in whatever order you want. I chose MJK. Probably should have done JKM. Isn't that alphabetical? KHAJKLM. Yeah, JKM. But it doesn't matter. Whatever you choose, these have to correspond. If I choose M first here, I have to choose K first here, because those correspond properly in the two different triangles. Okay, number 2. Kind of the same stuff. I can go statements and reasons here, and this one's almost identical. So the only thing here, which is kind of interesting, is that there are 4 congruent segments. You can see your 2 triangles. We have 4 congruent segments, so you can really order these any way you want. These are 2 isosceles triangles. I'm just going to choose it in one order that I would like. Now, here's why the 2 triangles thing is important. I could say ZW is congruent to WD, but that doesn't help me say anything about the 2 triangles being congruent. I made a congruency statement within the same triangle. I want to compare ZW to something in the other triangle. So I want to say ZW is congruent to ZS or to SD. Again, it doesn't matter in this case. They're all congruent. So I'll just put ZS. That's given. Why did I put a 2? Statement number 2. WD is congruent to SD. And I'm going to kind of bolt right through it. Hopefully you can see that as you go. And again, you have ample time to pause and do everything else on here. You have a lot of opportunities. Shared side, once again, ZD is congruent to itself by the reflexive property. Let's put reflexive. Okay, and now that I have 3 sides congruent, that's enough evidence. That's enough for triangles to say they're congruent. So again, that's what all that stuff means in the beginning. Because of side, side, side. And I don't know why I like to write the reasons first sometimes. Side, side, side. Let's see, we said that ZW was congruent to ZS. So when I do this, if I start with triangle ZWD, over here it would be nice to match up with that. I'll put ZSD over here. You very well could have put DSZ, but because of the way I wrote my statements and said these 2 are congruent, then I'm also saying these 2 correspond. So when they correspond, I want them to match up in the statement as well. That's by side, side, side. Okay, number 3, prove angle A is congruent to angle R using a 2-column proof. Now, this one's a little different because of what the proof says. And I've made the statement before, but when it tells you, when it doesn't say prove triangles are congruent, and it says prove something else, prove angles are congruent, prove segments are congruent, prove the triangles isosceles, something like that. And I'm telling you right now, because I've done 2-column proofs for a long time. I'm pretty old now, or whatever. I've done geometry. I can't think of a time when I haven't done a 2-column proof that still doesn't involve proving triangles congruent first. If I prove triangles congruent first, that opens up a lot of opportunities for you to do more things, because once you prove 2 triangles are congruent, like these 2, and you can tell I'm going to be able to by side angle side. Once you prove triangles are congruent, now you get to explore CPCTC, which means other parts are congruent. Once other parts are congruent, you can start saying a lot. You can say you have a parallelogram, you have, whatever it is. This one's pretty simple. You're just going to prove these are congruent after the fact. So let's go and do that and see if this makes sense. So first I'm going to say segment AN is congruent to segment RW, given. Oops. And all these will be given, by the way. They give us all this. Angle N is congruent to angle W. My G's aren't looking so hot. And finally, NG is congruent to WT. So here I have side angle side with side angle side. Now, this statement's still important. This statement's actually super important for the rest of it, because you have to correspond parts properly in order to make your other statements make sense. So I'm going to put triangle ANG, should have put NAG, is congruent to triangle, if A and G is here, as long as this is drawn the same way, I'm good, RWT. Because of side, angle, side, congruency conjecture. Now remember, I'm not done. Remember what they want you to prove. angle A is congruent to angle R. Now I can make this, and whenever they say prove this, this is like always your last statement too, because that's the last one you want to make. Your last statement is, he's guilty. He murdered him. Angle A is congruent to angle R. Why? Why did I do all of this? How does this help me draw this conclusion? Well, I know these two triangles are congruent. And remember, once the triangles are identical, that means they have identical parts. When we, I don't have it up anymore. Matching angles of identical triangles are the same. A and R are matching angles in these two triangles. These two triangles are identical, so these matching angles are the same. A is congruent to R because of C, P, C, T, C. Corresponding parts of congruent triangles are congruent. That is the reason behind it, and it is a valid reason for angles of a triangle being congruent. C, P, C, T, C works. Okay. Not only that, really, but also segment AG is congruent to segment RT, and angle G is congruent to angle T. For the same reasons, that's not what they asked us for. They just asked for angle A congruent to angle R. Those two are also true. Okay. Moving on, and I'm going to speed it up now. Okay, IE is congruent to GH, and so this is another way they'll do it sometimes, and it's actually funny. Normally they won't mark that stuff. If they tell you it here, they want you to mark it up. So that's pretty interesting. IE is congruent to GH. So let me actually write that. IE is congruent to GH, given. EF is congruent to HF, and again, normally they'd have you mark that. So I'm pretty shocked about that. Also given. And then they tell you F is the midpoint of GI. Not that I have to write that as a statement. You know what? Sometimes they do want you to write that as a given, and then you use that as a reason later. But I'm going to use this as a reason for something. It says, and this is one of those things where you can't assume that things are drawn to scale. F is the midpoint of GI. Now, F is obviously the midpoint of EH because EF is congruent to FH. We know that. We don't know that IF and FG are congruent. But they just told us that F is the midpoint of GI. F is exactly between point I and point G, which means F creates two congruent segments here and here. So you can make a statement that says IF is congruent to GF, and it's not because it looks like it or anything else. It's because they tell you F is the midpoint of GI. Now that's one of the things I put here. I just put midpoint to save you time. Midpoint. Midpoint, and in a book it might say definition of midpoint or something like that. But that's a reason behind that being true. So we can now mark that up. So now you have these two congruent triangles. Triangle EFI is congruent to triangle HFG because of side-side-side congruency conjecture. I got three sets of congruent sides in these two triangles. Make sure that makes sense. EFI from 2 to 3 to 1 is HFG, 2 to 3 to 1. That's tick marks is what I'm saying. Okay, 5, prove the triangle's congruent using a 2-column proof here. I got to, now just because you have right triangles doesn't mean you have HL. I'm going to debunk that right now, and in this case that's exactly what that is. PQ, segment PQ is congruent to segment NM, given, and I hate that they gave us all that. Well, I don't hate that, but these ones are kind of too easy. Angle Q is congruent to angle M. It's also given, but sometimes you're going to have something where it's like, these are both perpendicular segments here, so they create right angles. So maybe they put something like it's an altitude that's drawn, or create something perpendicular. And if they don't draw those marks, you can't necessarily put given if they don't draw them and you have to. So another reason might be 90-degree angles or whatever. If there are two angles that are 90 degrees, they're both equal. They have to be. If there are two angles that are both 50 degrees, they have to be equal. But that symbol represents a 90-degree angle. Statement 3, QR is congruent to MO. Excuse me. And we have enough information. We can say that triangle, I'll put PQR is congruent to triangle NMO because of side angle side. Now notice that I didn't put HL because I don't have HL. I don't have the hypotenuses given or proven to be true. Now I can prove them true. It's pretty simple. If you use Pythagorean theorem, you could say these two are true. But you don't have to. That's an extra step. I have side angle side right here. So make sure that you don't automatically say it's HL because you have right triangles. HL only exists in right triangles, though. It does not exist in non-right triangles. Okay, given AE and BD bisect each other. Now this one's kind of important because I want to make sure you know what bisect means. And in this case, it's not going to help too much because they bisect each other. What if it just said AE bisects BD? If it says AE bisects BD, it means this segment is drawn directly in the middle of BD, as in this point C would only create identical congruent segments between BC and ED, not necessarily for AE. So that would mean BC and CD are congruent to each other. Now, in this case, now this is not given either. Right now I'm just going to put bisector. I really should put segment bisector. Like here, I think I put that. Segment bisector. I could have put AE, I could have put this thing as well right here. I just don't have enough room, really. It's a bisector. Now, it doesn't just say AE bisects BD. It says they bisect each other. So segment BD, although this is cut in half, this also cuts this guy in half equally. So AC is congruent to CE as well for the same reason. Bisector. Really, segment bisector. I want to get in a habit. And finally, okay, I don't know these lines are parallel. Yeah, they look parallel, but I don't know that. But what I do know is that this is a straight line. And I do know that this is a straight line. And when straight lines intersect, they create vertical angles. They create them here, but those aren't in the triangles. They create them here and here. And as we know from our angle relationships and properties, excuse me, vertical angles are congruent. So right now I'm just going to put vertical angles to make sure you know that's what we're looking at. Okay, now this part's going to be tough. I don't want you to say angle C is congruent to itself. These are two different angles. I want you to be unique to the triangles. In this case, this is where you use a three-letter angle assignment. Angle ACB. Angle ACB. That means A and B are the endpoints, C is your vertex, is congruent to. Now, it doesn't matter which way I write it. I could write DCE or ECD. But I like to write it in the order of parts which correspond. If AC corresponds to EC, then I want to write it in that way. If I wrote ACB here, then I want to write ECD over here. Because when you make your triangle congruency conjecture, you can write it in that order. In fact, that's exactly the order they write it in. So vertical angles there. I have enough information to now say triangle ACB is congruent to triangle ECD. Because of what? What do we have? We got side, angle, side. Side, angle, side. So side, angle, side congruency conjecture right there. Okay. Moving on, number 7. We are given the angle BAC is congruent to angle DAC. And again, they were very, very nice of you. It was very nice of them to draw your angle relationships there instead of making you do it. This is the one where they're very nice. AC, segment AC is perpendicular to segment BD. Now that means a lot of things. It doesn't just mean there's a right angle there, but in a straight line with supplementary angles, if one is 90 degrees, the other is 90 degrees. Now this is one of those examples where this is not given, and I actually had to draw that. But this does show that right there. So maybe that's enough information to say those two are congruent. But if they didn't have a drawing, it might be really tough to look at and work at. Prove triangle ABC is congruent to triangle ADC. Here we go. Start with the given. Angle BAC is congruent to angle DAC. And then they tell us Okay, they tell us AC is perpendicular to BD. That creates these congruent angles. So I want to create another set of congruent angles here that I know now. Angle, I'm going to put ACB, that right angle, is congruent to angle DCA. Now, some teachers and some scores and such, they want you to add a different line of dialogue and say these are 90 degrees because of this reason. I'm skipping that statement, kind of. I want you to know that they are 90-degree angles for that reason. That AC is perpendicular. That's the perpendicular sign to BD. Okay, either reason works for me, honestly. Enough to say that those two are congruent. Again, you're building up evidence. That's good supportive reasoning. In fact, I don't know if I put perpendicular here. Okay, 90-degree consecutive angles. I kind of did this. This is the same thing. When you have angles which work supplementary in consecutive order, such as these guys right here. Oh, gosh. Then that means, I don't even know where I am anymore. Redo. What the heck happened? I have no idea what just happened here. When you have them working in consecutive order there, then that means that those two are congruent for that reason. Okay, and 3, I have a shared side in both triangles. That means these are congruent to one another. Or, well, they're the same thing, but they're in two different triangles. They exist in both different triangles. That's why we write this statement. AC is congruent to itself. It is a no-duh. I understand that reflexive property is no-duh. But if you're going to build up evidence, and you are talking about two different triangles, you have to treat them like they're two different triangles. And in this case, they are congruent for that reason. Now, that's not reflective. It's not mirror. It's nothing like that. That's not what it means. In fact, I don't really know. I wish I had a better definition for the word reflexive that had to do with the word reflex. ABC is, I guess it would mean instinctively. It's reflex to know that they're congruent. Now, I don't know. Triangle ABC is congruent to triangle ADC because of angle, side, angle, with angle, side, angle. And again, this is another right triangle that doesn't have HL, so it's, it is what it is. Okay, PQ is perpendicular to QS, so again, they gave you a right angle, very nice of them. RS is perpendicular to QS, another right angle. T is the midpoint of PR, proved triangle. PQT is congruent to triangle RST. So I kind of got to work quickly here. People are going to pile in soon. Step 1, I'll say angle Q is congruent to angle S. Because they're not shared anywhere else, I can use one-letter assignments like that. Not given. Shoot. I'll just put 90 degrees. Running out of time. 2, okay, they do have T as the midpoint of PR. Now, this is an example. T is the midpoint of PR. They do not say T is the midpoint of QS. So you cannot say these two are congruent. They don't tell you that. They don't. They do tell you PT is congruent to TR because of this midpoint reason. So you tell them PT is congruent to TR. I really should have put RT if I'm arguing that I should correspond things properly. Because of the midpoint. That segment. Bisector and midpoint both exist as valid reasons. Midpoint, again, also works for segments. And finally, I do have straight lines going through and intersecting with each other, so I do have vertical angles here being congruent. So here's where I have to use 3 letters, because that T is shared in both triangles. So angle, I'll put RTS is congruent to angle PTQ. Vertical angles are congruent. So finally, PQT, triangle PQT is congruent to triangle RST. I'm using the statement up here by angle, angle, side, angle, angle, side. Again, another set of right triangles. It's not HL. I'm surprised none of these were HL. And the final one, got to rush through this one. Prove quadrilateral VWYZ is a kite using a 2-column proof. So again, this is one of those things where, how do I say this? where you have to prove triangles congruent first. When you do that, you can do a lot of exploration to prove that it's a kite. So I'm going to use what I'm given here. I know angle Z is congruent to angle W. Given. I also know that angle ZVY congruent to angle WVY reflexive property here, Vy is congruent to itself. Okay, now I have a triangle congruency statement I can make. ZVY is congruent to WVY. Triangle WVY by angle, angle, side with angle, angle, side. So I have angle, angle, side here. Now what that helped me do, again, running out of time, so I'm going to do it quickly. What that helped me do is now make other congruency statements, and this one's kind of going to be bigger. I don't have much room. This is going to be my CPCTC reason. Now I know, and I'm going to use different colors here, that VW is congruent to ZV is congruent to WV. ZV is congruent to WV. They're corresponding parts. I also know that ZY is congruent to WY. These are corresponding parts here and here. Again, CPCTC. Corresponding parts of congruent triangles are congruent. So ZV is congruent to WV. And I'm going to do this all in one statement. And ZY is congruent to WY. Because CPCTC, corresponding parts of congruent triangles are congruent. And finally, quadrilateral, that's a symbol. VWYZ is a kite. Kind of, I mean, you're going to have to list your own reason here. This is one of those that didn't exist on the other one. Like I said, it's super specific. The reason is kind of the definition of a kite. Consecutive sides, two sets of congruent sides that are like next to each other, right? I could have done a lot more. I could have drawn altitudes here and said perpendicular, one's a bisector to the other, perpendicular, stuff like that. I'll just put definition of kite for now. I don't really know if that's going to exist on your final, but that's another good practice thing. You still practice your triangle congruency alongside it. Okay, and that's all the time I got. I hope all that made sense as you went along. Again, please rewind and fast forward and do as you need to make sure this makes sense to you. This is for your benefit. Practice them on your own as well. Do some other ones online. Do whatever else. But hopefully this is very good stuff for you. I know we didn't go over any parallel ones. That was for the sake of the problems that were given to you. But please practice some of those as well. Make sure that all makes sense. I want you to get this stuff and see why these symbols are what they are and why we do what we do with them.